Hello, my name is Yukang, and I'm here to present RF convergence with GNURadio. So today's talk consists of 5 parts. First, I will introduce RF convergence, then I will give an example of an RF convergence system. Next, I will show implementation of example system in GNURadio. At the end, I will provide the results of the over-the-air experiment using it and summary of the content today. First, let me introduce the concept of RF convergence. Before introducing RF convergence, we need to realize the problem we're facing nowadays. Spectral congestions caused by increasingly crowded wireless domain is a major concern, especially for telecommunications. As you can see in the picture on the right, there are so many communication users, and they probably share the same spectral allocation. However, spectral resources are limited for so many users. In worst case scenario, it can cause severe loss in communication performance and lead to system failure. In worst case scenario, AT&T, for example, it will slow your data speed if you don't have premium data available. So here comes a promising solution to reallocate and share spectral allocation, and that is RF convergence. Now let's talk about what RF convergence is. We use resources jointly for radar and communication systems. For example, bandwidth allocation, we use the same spectral allocation for both radar and communication signals. In order to make it work, we are developing multifunction RF systems, including multifunction transceivers for both radar and communications, which transmits and receive joint radar communication signals. RF convergence system can improve spectral efficiency and reduce external interference and enable new system capabilities. Here are some ideas of the RF convergence system. So there are several automobiles. So it can detect the distance between vehicles using the radar from pre-collision system, and it can also receive communication signals at the same time. For example, if another car wants to change lanes, it can receive the information and stop accelerating and let it in. Next example is Google's idea of ATAPS Soli, still under development. It uses 2x4 antenna as a radar to recognize gestures while talking with another user. For military systems, for military systems, planes can send and receive radar signals while communication with other units using the multifunction receiver. Next part, I will provide an example of a simple RF convergence system. The block diagram, as you can see here. So it decodes communication signal and estimates target range simultaneously. And it uses temporal negation to disentangle signals. It can jointly improve performance of both systems. So in this case, the transmitted signal consists of a strong communication signal and a weaker radar signal. So the communication signal can be decoded easily. As you can see, here's a result. So the radar return with a clear peak can be easily seen after temporal negation. So about temporal negation, it is the key kernel that enables RF convergence. It can disentangle multiple signals from a composite signal, and it removes one source at a time. It helps implementing successive interference cancellation in this system. So it decodes the strongest signal from the received signal and removes it and repeats it multiple times if there are multiple sources. So it can be iteratively done until all signals are sufficiently interference-free. So here's a block diagram and the equation for temporal negation here in slide. And here we'll show how we implement the system in GNURadio. So here is an illustration showing the complexity of RF convergence system. It is extremely difficult to implement simple RF convergence system in RF hardware because it is a relatively new area of research, and the system design is undergoing rapid advancement of the RF convergence system. And the algorithms here are computationally complex and novel, and there is no ready-made hardware implementations, and it requires both algorithm and hardware expertise. So there is an urgent need for tools to facilitate hardware implementations of RF convergence. So here we implemented the temporal mitigation block as previously mentioned. So as we mentioned earlier, it disentangles multiple signals from a composite signal and remove one source at a time. It can be iteratively implemented for multiple communication users by using the spatial temporal degrees of freedom. It can greatly improve performance of multiple channel, multiple user receiver. And here's a link for which contains our work down below. So here is a flow graph of the GNURadio implementation. So we use GNURadio to easily deploy RF convergence system on RF hardware, and it is extremely important for rapid development, testing, and evaluation. So the implementation here is driven by the developing the new temporal negation GRC block. And here's a magnified version of the GRC flow graph. And next, we'll present the result of the over-the-air experiment using USRP. So here we have a 1 antenna transmitter and a 4-channel receiver. For the parameters of the relative power levels, the radar is -10 dB and communication signal is 10 dB and the noise is 0 dB. And we use a LFM radar waveform with time bandwidth product of 100. For communication part, we use simple BPSK communication signals, and both signals overlap in spectral and spatial domain. So the setup is shown in the picture, and again, we provided the link of our work. And next, I'll show you the results. These are the range Doppler map of the radar return. The one on the left is the radar return before temporal mitigation. So here the communication signal is not removed yet, and the one on the left is after the temporal mitigation. So here the communication signal is removed. So as we can see, the target point is very hard to recognize for temporal mitigation, but it can be easily seen after temporal mitigation. And in the end, there's a summary of today's content. So we introduced RF convergence system, and we showed the implementation of the system in GNURadio, and we showed the experiment result over the air. And that's it.
Thank you very much. So there's one question, more of a comment from chat to start off with, and it's that some of these techniques reminded this audience member of OFDM radar, and they were wondering whether you had looked at all into that sort of space.
Sorry, can you repeat the question?
Have you looked at all at OFDM-based radar and some of the techniques there?
So OFDM radar, I'm not sure. So here's the point of our work. So we're here to solve the spectral allocation problems. That's our main focus. So we share the communication signal as you can see, especially nowadays for 5G, we have very limited spectral resources. So if we can share the spectral allocation with radar, we can have more spectral resources to use. That's the main point of our work here.
Great, thank you. Are there any other questions here in the room? No? Thank you very much then.